Chapter 15, Section 2 talks about our other definitions of acids and bases. We already mentioned Arrhenius, who says that acids, when dissolved in water, increase hydronium ion concentrations, and bases increase hydroxide concentrations. So there's a couple drawbacks to that. One is that they only apply to aqueous solutions, so only if you dissolve them in water do you know whether they're acidic or basic. And then the second thing is that not all bases donate hydroxide. So for instance, ammonia doesn't have a hydroxide ion to give away. So it couldn't give away an OH minus. So instead, we've since replaced them or added to the definitions with the Bronsted-Lowry definitions. So they're a little bit more modern. A Bronsted-Lowry acid is going to be a proton or H plus donor. So any substance that can give away an H plus ion is going to be an acid, a Bronsted-Lowry acid. So like in this equation here, H2SO4 becomes HSO4 minus. That means that it must have given away one of its H pluses. And if we look at the water that we combined it with, it becomes H3O plus. So the H2SO4 gives away a H plus to the water to make the hydronium and the HSO4 minus ion. If something is monoprotic, that means that it donates one proton. So like nitric acid only has one hydrogen, so it could give away one. Diprotic means it has two. Triprotic then means it has three. And each of these protons gets given away in a separate step. So it doesn't happen all at one time. It would occur one equation, and then you would have to do a second equation where you would get rid of the next one. So Bronsted-Lowry acids are proton donors, which means that Bronsted-Lowry bases are proton acceptors. So here we have ammonia, NH3, combining with water. And on this side of the reaction, we can see how they changed. NH3 becomes NH4 plus, so it gained an H plus, and the water became OH minus, so it lost an H plus. So in this situation, water is the acid, it's the proton donor, and NH3 is the base because it accepted one. Now if you notice, in this situation, water was the acid. In the equation before, it was the base. Anything that can act as either an acid or a base is referred to as amphoteric. A conjugate is going to be the product of an acid-base reaction. So a conjugate acid is the acid that gets formed after a base accepts a proton, and a conjugate base is the base that's formed after the acid donates a proton. So you have your acids and bases as your reactants, and then your conjugates will be your products. And then just kind of a trend that we see, the stronger the acid or base, the weaker its conjugate will be. So here in this particular equation, this was our ammonia and water equation. Ammonia was the base, and what it becomes, the NH4 plus, is its conjugate acid. The water was the acid, and what it becomes after it gives away the H plus is the conjugate base. So this would be one conjugate acid-base pair, and this would be one conjugate acid-base pair. The last set of acid-base definitions are Lewis definitions, and just like when we were drawing Lewis structures, we were filling in electrons, that's what these ones deal with. So a Lewis acid would be a substance that accepts an electron pair, and Lewis bases are ones that donate electron pairs. And the last thing in this section are acid ionization constants, or Ka values. This is our equilibrium constant for a reaction where an acid donates a proton to water. And a Ka value is kind of like pH. It's going to tell you how strong or weak an acid is. There's a table in your book on page 557 that lists a whole bunch of different Ka values. So the larger the Ka, the stronger the acid is. In this particular equation, we've got acetic acid combining with water to make H3O plus and the acetate ion. So we write our Ka expression, which is aqueous products divided by the aqueous reactants. So we set it up with H3O plus times the CH3COO minus, and then divide it by the CH3COOH. We leave out water because it's a liquid, so its concentration is not going to change. We only include the aqueous ones. And then if we were given the values, if we were given these two values, all of these concentrations, you would then be able to calculate your Ka value. Or maybe sometimes you'll be given Ka and 2 of the 3 variables, and you would solve for the third one.